Start.
Yeah.
Welcome to the ICTS String seminar. Today we have Sachin Jain, who will talk about anyons and 3D bosonization.
Okay, thank you very much for this opportunity to speak, and especially thank to Anupam for all the trouble he took. Okay, is there a pointer? Is there? Yeah. So I'll be talking about anyons and 3D bosonization, and I'll be mostly the theories that I'll be interested in is Chern-Simons matter theories in 3 dimensions. And what I'm going to show in this talk is that correlation functions of operators or any spinning operators can be mapped to how can I map it to the free theory correlates. Okay? That is what I'm going to discuss.
Change it from this one. Yeah. Right.
Okay. So as I just said, it's a developed systematic method to compute endpoint correlation function of arbitrary spin in Chern-Simons plus matter theories. We'll see that the anyonic nature of CFT correlation function comes out very naturally here. Also, this anyonic nature makes this 3D bosonization manifest. This work is based on this archive preprint. Prabha, Bibhut and Asna, these were 5th-year undergrad students, and Dhruva, my current integrated PhD, just beginning integrated PhD student. So these are also based on the previous work. Abhishek, who is a PhD student, he is graduating this year. Ranjan, my earlier postdoc. Aditya, Yatharth, 5th-year students, and Amin Nijami from Ashoka University. Roughly, this 3D bosonization duality is a duality between two theories. So it's roughly maps theory of bosons coupled to Chern-Simons with a theory of fermion coupled to Chern-Simons. It's a strong weak field theory duality. Non-supersymmetric as well as supersymmetric version of this duality exists. This duality has been checked extensively. It's also these theories are also gives a non-trivial example of conformal field theory. These theories are also dual to higher spin theory in 1 high dimensions, and these are also exactly solvable large n. That is one of the claims. Okay. Here is a brief cartoon. Critical bosonic theory was conjectured to be dual to Vassiliev A theory in 1 high dimension ADS, and free fermionic theory was conjectured to be Vassiliev theory B. If I couple with the Chern-Simons, so in the bulk it was known that there is a parameter theta parameter which interpolates from Vassiliev A to Vassiliev B. Later on, motivated by this, later on people discovered that the in the field theory side, this Chern-Simons gauge field does this job of interpolating from critical boson to free fermion. So, in the free fermionic theory, for example, I have single trace operator, all the spin 0 and all the spin s currents whose scaling dimension is delta s is equal to s plus 1, and these spins are conserved for any spin. Also for spin 1 and spin 2, where it will always be conserved. I have not just indicating s greater than 3 that this is also conserved. That's why these are higher spin theories. These are dual to higher spin theories, where you have here you have all the higher spins are conserved. Whereas if you couple it to Chern-Simons, up to spin 2 it is conserved, but beyond spin 2 these are weakly broken, and weakly broken in the sense this is 1 over n. The del dot js is non-zero at 1 over n. Okay, this is what is non-conservation, and slightly broken means. So just to make this point more clear, what is the meaning of conserved current versus non-conserved current? Watt-Takase identity for conserved current will have, let's say I'm considering TJJ, this stress tensor spin 1 and spin 1. then the Watt-Takase identity, which is a conservation Watt identity, will have a delta function at the location of other operators. Okay. Similarly, I have just given two examples. You see that there are delta functions. More precise details I have not written here, how exactly the derivatives are distributed. But what is important here, there is delta function. So, you know, del dot t is 0 away from other insertion. That is the meaning of conserved currents. Whereas weakly conserved or non-conserved current means del dot j is non-zero even away from other insertions. For example, spin 4 current, it will be non-conserved and it will have spin 1 double trace operators appearing on the right hand side, but there is no delta function here. So this is non-zero everywhere. So for example, if I try to calculate Watt-Takase identity, in the large n limit, this will become a product of two different 2-point functions. Okay, this is a very important distinction that will be useful later. This is a summary of the known result. This was done in Gyombi, Prakash, and in. This is a purely conformal field theory analysis. I'll just focus on focus on all the non-zero spins. The claim was that for any CFT, just using conformal invariance, what it was shown that 3-point function of conserved current contains 3 structures. Okay, where by FB I mean calculate this 3-point function of these 3 conserved currents in the free bosonic theory, in the free fermionic theory, and this is a parity odd structure that is also possible if you are in the range when any addition of any 2 spin is greater than or is equal to the other spin. Okay. However, when this triangle inequality is violated, then you do not have the parity odd piece. You have only parity even piece. Okay, 2 parity even piece. For example, if I consider J4, J1, J1, 1 plus 1 is less than 4. So that is an example of something outside the triangle. Okay. So and then in that case, there will not be any parity odd stuff. However, let's say I consider TJJ or TTT. This is the example of a inside the triangle, and it will have all the 3 structures. Later on, what Maldacena and Joviudov, they showed that now instead of exactly conserved current, now let's say the currents are not exactly conserved but weakly broken. In the sense I have already discussed, it is weakly broken at it goes as 1 over n. In that case, what Maldacena and Joviudov showed that irrespective of the spin triangle, you always have 3 structures. Okay, for this class of theories, there is a free boson, free fermion, and the parity odd structure. Always there are 3 structures. For a particular class of theories called quasi-fermionic theory, which is Chern-Simons theory coupled to critical boson. Critical boson is just the you couple free boson theory with the phi to the 4th theory. It's a Wilson-Fisher fixed point of the free bosonic theory. All these things are at large n. Or Chern-Simons theory coupled to free fermion. These are examples of a quasi-fermionic theory. In that case, these coefficients are also explicitly determined in terms of some parameters lambda tilde and n tilde, which appear in the non-conservation of these higher spin currents, and which will also be related to the tube coupling in the Chern-Simons matter theories. But this is the result that was pointed out by Maldacena and Joviudov. Here, I just want to emphasize that what you get that even outside the triangle, you get a parity odd structure, and this appears only because there is a non-conserved current. Okay.
But somehow it's a same order in n tilde.
Yes, it's a same order in n tilde.
But I thought in the limit where you when n tilde goes to infinity,
yeah,
then they become conserved currents, right?
That is right.
So somehow in that limit, how do you see that gamma is absent?
How do I see?
I mean, because there's a parameter, there should be a way of scaling things such that parametrically you see that it is suppressed, right? That the parity odd structure vanishes.
Yeah, in this case, it is not. Let's say I have. In this case, it is not directly visible. This is. Let me see. If I take n goes to infinity, these all the three structures are actually
of the same
order.
Yeah.
And the way they come actually is, what I showed was that due to, let's say, one of the spin being non-conserved, the Ward identity, what you will find out is a product of two point functions. Yes. There was a factor of 1 over n, and then each 2-point function goes at order n, and then so n square by n gives the same ordering as n. That's how the counting goes.
Yeah, that I understand. For the del dot j is some jj.
Yeah.
But shouldn't there be some way of taking a limit in this correlator such that you see that the parity odd structure vanishes outside the triangle in the strict limit that the currents are conserved? Shouldn't there be some way to see that? Maybe. But I thought it's not lambda tilde, which is the 1 over n tilde, which is the.
It's order lambda tilde by n instead of order 1 by n.
Here, lambda tilde.
So lambda tilde goes to 0. Yes, I can understand that.
Then the parity of stuff
free theory, and then everything is conserved.
Lambda tilde goes to 0. Lambda tilde goes to infinity is a free bosonic.
Yeah.
In these both limits, you get what is the pure boson or pure fermionic, but in between you get.
Yeah, but what Rajesh is asking, is there a way? I should be only just keeping lambda tilde as it is, but taking n tilde to infinity.
Because that's the context I think you're going to talk about, right? Lambda tilde, you're kind of keeping arbitrary.
Yeah.
But the soft breaking is coming from the 1 over n tilde.
Yeah, soft breaking is coming from 1 over n. For me, the way I'm going to think about, that's a good question. I should think about it. But the way I'm going to think about is the other way around, that, if I want a free theory, then lambda tilde, I'm going to set it to 0. But I should think about it. I don't have a good answer right now. So here I just once more emphasize that the parity odd structure appears because of the non-conservation. Okay. So what we are going to do is that we are going to analyze things in momentum space. Momentum space CFT coators are interesting. They have connection to S matrix cosmological correlators, etc. For example, double copy like relation. Sorry, here it is little smaller, but in my screen it was a bit bigger. Sorry about it. What I wanted to say is that there is a very interesting connection with the S matrix structure and the momentum space CFT coators, and that is that if you consider, let's say 3 spin 1 current correlator, if you square, you will get a 3 spin 2 current correlator. Spin 1, that's a stress tensor 3-point function, and this you can do it for arbitrary spin. Okay. However, today's talk will be focusing on Chern-Simons matter theory and application of momentum space correlators in that theories. Okay.
Does this hold also for half integer spin some currents? This triangle, this square, this doubling relation.
So actually, right now, one of my students is doing. I think there are 2 sectors to it, which I'm going to come to in a minute. In one of the sector, it is very clean. I think there it works. I'll come to in a minute in what sector it works. I'm sorry. Again, it's very small.
Maybe use on this.
It is. Is it? Yeah. It's actually.
Yeah, you have to exit full screen and then fit with or something.
Yeah.
Fit to with.
Sorry. So it's now visible, right?
Probably you can even go now to full screen.
How do I do that? One second, sorry. View. Full screen mode. Yeah. Oh, it's not. Okay. So this is okay, right? But probably it will not. It will not do this. No, it does. It does. Okay. Oh, okay. I have to scroll it. 1 second. Yeah, okay. I'll just stand here and. To describe our result, we need to introduce some notations. And first, let me remind you that the word identity has the delta functions at the locations of other operators. Note, I'm writing word identity for TJJ, and here the right hand side JJ 2-point function appears. In 3 dimensions, JJ 2-point function can be both parity even and parity odd. Okay. At separated point, right hand side is just 0. But now in momentum space, you see, in momentum space, you can no longer ignore this word identity, meaning you cannot, there is no notion of working at separated points. So you have to consider this word identity always. To obtain CFT correlator in momentum space, unlike in position space, here you have to solve some second order differential equation, which is roughly action of special conformal generator on the correlator. And in the right hand side, what you get is precisely this transverse word identity. Okay.
Is it easy to go back and forth between the momentum and positions? Is it easy to go back and forth between momentum and position space?
By doing Fourier transform?
Yeah.
No. By direct Fourier transform, it's not easy. But once I get this result, then I'll be able to map it to the position space result, as I'm going to discuss.
So, I mean, those singularities, suppose you want to, give you the position space correlation function, right?
Yeah.
With some singularities, and you want to make a Fourier transform.
Yeah.
That is okay, or that causes problem?
Yeah, just doing the Fourier transform is not that easy. That's not, it is much more easier. You know, I have never tried to do that Fourier transform, but I suppose if I allow for, so the way in position space it is done, you write down all possible terms that is allowed by conformal symmetry that you can write down directly. Then you impose this conservation. That at separated point, these are conserved. But let's say, as you say, I don't impose that conservation. I put in that they have this delta function. You can work that out, and what you will be able to get is that with certain, it will fix the coefficients of certain thing.
Yeah, but suppose you have then integrated and actually gotten the T correlation function of T with some other thing,
yes,
right?
Yeah, yeah.
Which will have these singularities, right?
Yes, yes.
Even in 2 dimensions, right? They have this 1 over z minus w squared kind of singularity.
Yeah, yeah, yeah.
Now suppose you want to make a Fourier transform to go back to momentum space, right?
Yeah, yeah.
What I'm asking is that, is it clear that they are completely unambiguous the way you integrate through those singularities?
You see, if I'm thinking from a perspective of, let's say, if I'm thinking from the Lorentzian perspective, then clearly it will depend on like how do you enclose the singularities, I epsilon prescription. And in momentum space, although that has not been done yet.
Normally in position space, one doesn't talk about I epsilon, but I guess some version of.
Yeah, there is some version of, you can define a particular ordering in position space.
Well, I epsilon is more infrared, right? From the worldsheet perspective.
Right.
Whereas these are ultraviolet singularities, right?
Right.
On the. These will be like short distance.
This will be like short distance, short distancing. I'll tell you. So,
you have different sheets when you have, I mean, when you have to specify.
Which
sheet you are in when you go around.
Go around the singularity, but yeah.
In the Euclidean, it should not be a problem.
Yeah, in the Euclidean there is no set. There is only There is only one thing. There is no ambiguity.
But even in the Euclidean, those singularities are there, right?
Yeah, those singularities are
1 over z minus w square singularities are there, and you have to integrate through them somehow.
Yeah, integrate them through somehow. That exercise actually I have never done, and because of these issues, it was not never clear how to do those integrations. But what you can do is that what you can do the following: that let's say you have a free scalar field theory, you calculate in the Poisson space a correlator, you get something 3-point function. Now you just redo that calculation in momentum space, and you get a result. And you can check that by solving this thing, you get exactly the same result. So that is one way. But directly starting from Poisson space to momentum space, I think that's a little I have not really thought about. But the issues will be like singularities. How do I deal with them? That will be one of the things. Yeah. But what I was other thing I was saying, if I go to the Minkowski space, I think there's something very interesting happens. If I just solve this water entity in momentum space, in Poisson space, what you do is that you just write down a 3-point function, which is a unique structure. Let's say a 3-point function of scalar. You just get only a unique structure. But in momentum space, even for scalar, you will not get unique structure. You will get 4 different structures. Then, then if you want to find out which of that 4 solutions correspond to the Poisson space answer, you have to check OP consistency. In Poisson space, OP consistency is very, very automatic, but in momentum space, it is not automatic. And then you'll be able to find out which answer corresponds to the Poisson space thing. In one dimension, this is something we are investigating right now. In one dimension, it turned out that all the 4 solutions of that scalar thing actually are 4 different Minkowskian possibility of the 3-point function that is allowed in Poisson space. So that is one connection to the singularity, at least in I-epsilon prescription.
You're saying 4 different possibilities or 3 different possibilities, again, the different sheets?
Yeah, different sheets. So for 3-point function, you can have 8 different possibilities, 2 to the 3, but 4 of them are identical to other 4 by some complex, simple conjugation. And momentum space, in one dimension, at least you can show that they are precisely equivalent to what you get by solving these equations. 0 plus 1 dimension. Yeah, quantum mechanics. Yeah, quantum mechanics. Yeah. So,
sorry.
Yeah.
You said, but OP consistency fixes it, you said, in momentum space.
Yeah. Poisson space. Yeah, momentum space, right.
In momentum space, you said it is fixed. But then you said again that these 4 different structures correspond to different Minkowski space continuations.
Yeah. So what I mean is that suppose I'm in the Euclidean space.
Yeah.
And in the Euclidean space, if I calculate a quater in Poisson space, I get a particular OP thing, right? Yeah. And that, if I translate into the momentum space, that corresponds to only one of the 4 quater. But now coming back to the Minkowski space, what the calculation till now we did, we just took a free scalar and then computed in the Minkowski space and the Euclidean space, and also did this analysis. And in the Minkowski space, using those I-epsilon prescription, we were able to reproduce all the 4 structure. But the question what exactly is the OP consistency then mean? That part in one dimension I have not yet understood. But I believe this story, there is some connection to it that I have not yet understood. I'm not. Minkowski says I have not.
You're saying maybe you're on this thing, the OP consistent. Yeah, Minkowski OP consistency is probably a little more tricky.
Yeah.
Because the light cone singularities.
Yeah.
And
there's a little more tricky.
So you maybe okay.
We have not yet thought about it. It's just kindly we are just trying to understand. Just one side comment is that is very interestingly these are also related to cosmological correlation function in D-4. If you consider the Bunch-Davies vector, the correlation function that you get is precisely the Euclidean correlation function, the one that is analogous to Euclidean correlation function, and that is consistent with the OP consistency. But if you remove the OP consistency, what you get is precisely the alpha vector correlation functions. So that's just a side comment. momentum space, solving this differential equation is not a very trivial task, and one of the reason that was one of the reason not much progress was done. But if you realize that this 3-point function can be broken into two different pieces called the homogeneous and the non-homogeneous pieces, then the actually structures become much more cleaner, and then the progress we will be able to identify which part is more difficult, which part is more easy to solve. So I'll explain what is this homogeneous and non-homogeneous things in a minute. So so as I said, this is so the homogeneous piece is something where the word identity is just 0, even at the coincident point. This is the homogeneous piece, okay? And the non-homogeneous piece is something which saturates the word identity. So particular solution of the word identity, exactly.
Homogeneous is difference between two
particular solution, is a part which actually is exactly gives you, just 0. Okay. Yeah, two particular solutions will differ by homogeneous solution, but in our calculation, we will be able to identify what exactly is a homogeneous solution and what exactly is non-homogeneous solution. So we'll have a very clear distinction.
The homogeneous ones, ignore the contact
terms. The homogeneous ones?
Yeah, they ignore the contact terms.
Yeah, homogeneous ones do not see these word identities at all. So these are the part, as you're right, it ignores the contact term. And from the Poisson space perspective, I'll show what do they mean. Okay.
Normally, the whole thing is called word identity. Right?
Yeah.
Right hand side. So when you like.
No, here, what do I mean by word identity is that, this whole thing is the word identity. What I mean, I'm sorry, what I mean is the this delta function thing that I'm calling as the word identity. Yeah.
Right hand side.
Yeah. Okay. So in Poisson space, we do not do such distinction. One more comment is that transverse word identity is generally unique. Okay. For example, if you take free boson and the free fermion, calculate their word identity, the conservation word identity. By transverse word identity, just del dot t jj. That is what I'm referring as transverse word identity. Okay. That's a language in the momentum space. There is a part that is parallel to the momenta, that is a longitudinal piece, and this is the part which is not parallel. The parity even, so you see that if I consider the parity even word identity, then I have one even non-homogeneous solution, right? To the word identity, k kappa acting on the correlator gives me the word identity. So if I consider the word identity or this part to be parity even, I get one non-homogeneous parity even. And if I consider this word identity to be parity odd, meaning I showed that there is a tjj had jj 2-point function in the right hand side. If I consider jj to be parity odd, then I get one parity odd non-homogeneous thing. And it is easy to show that this non-homogeneous parity odd term will always be a contact term. And this thing was missed in the Poisson space because they always work at a separated point. Okay.
Another question.
Yeah.
A contact term in position space necessarily doesn't translate to a contact term in momentum space.
Yeah, when I say contact term means contact term in the sense of Poisson space. If you transfer it into the momentum space, those will be polynomials in momentum space. Okay. So wherever I refer contact term, the contact terms in the notion of Poisson space.
Okay.
So it is easy to show that if I'm inside the triangle, there are two homogeneous solutions to the word identity. One of them is parity even and one of them is parity odd homogeneous answer. And then there are two non-homogeneous solutions, one parity even and one parity odd contact term. So this gives the simple proof of the tree structure earlier that was seen in the Poisson space. Okay. Now outside the triangle, the story is a little more complicated. Yeah, 4 term, and one of the term is a purely contact term that was not seen in Poisson space, meaning people were always concerned with the separated point, so they did not see this.
So J has an extra, these are 4 possible terms which can appear in the 3-point functions.
Yeah. One of them is parity odd contact term that was missed. Now, outside the triangle, things are a little more interesting. One can show, go ahead.
So the point is that, like you're saying that compared to the thing that you showed in this multi-difference kind of.
Yeah.
You have one more term, but it's made of delta functions.
Yes, precisely.
And that is determined by what? Its coefficient?
It just determined by the water entity. So instead of the JJ 2-point function parity, even if you put it parity odd, the JJ 2-point function in 3 dimension, parity odd part is by itself a contact term. So that leads to a non-homogeneous term which is contact.
But is it also given by this theta, lambda, theta that you say?
Yeah, you will be able to find out using higher spin equation. You will be able to actually constrain their coefficient as well. But those were not considered because coefficient space you work at separated point. So those were not considered. Yeah. But we will see in one context it becomes totally clear where it can come from. Yeah. Yeah, any point function.
But we are only interested in 3-point function.
Right now in 3-point function, but I'll go to the 4-point function. Right now I'm doing a purely CFT analysis. Purely CFT analysis in momentum space for 4-point function is very, very hard and no one has yet done. We are trying to think about it. But this homogeneous, non-homogeneous thing is also will be very useful there. This distinction will be very, very useful as I'm going to show now, okay? Outside the triangle, you can show that the homogeneous structure cannot exist. It's a one-line proof. It's just basically outside the triangle, any homogeneous structure will not be consistent with the OPE consistency, okay? And you can show that the homogeneous structure cannot exist. And this gives a simple proof of non-existence of parity odd structure outside the triangle, okay? In the earlier slide, I said that parity odd non-homogeneous structure is a contact term, parity odd homogeneous structure is fine. But outside the triangle, you see, there is no homogeneous structure that can exist. So this gives a simple proof that the parity odd homogeneous structure cannot exist, okay? Then you can ask, if I have only unique water identity, then how can I have 2 different solutions, okay? Because outside the triangle, I also have 2 parity odd, parity even answer, free boson and the free fermion. Interestingly, you can show that the water identity outside the triangle for free fermion and the free boson are not identical, okay? However, inside the triangle, those were identical. Outside the triangle, they are not identical. And this gives the 2 non-homogeneous parity even answer, okay? This proves the earlier count that people saw. Yeah, so this is one simple way to see the counting. So if I am using D-Sitter4 to calculate this correlator for CFT, the homogeneous part corresponds to W cube, the while cube term. As you can see, this while cube term cannot contribute to the 2-point function. So hence this corresponds to just purely a 3-point function, and this is the homogeneous thing, okay? Non-homogeneous even will be the Einstein gravity. And this will also contribute to the 2-point function. So this is what is the non-homogeneous even. W square W tilde is the homogeneous odd contribution. And W tilde, which will contribute to again 2-point function of TT 2-point function parity odd. And this is a non-homogeneous odd. And you can find out that this is a contact term, okay? This is the distinction. So roughly, non-minimal coupling in the bulk correspond to the homogeneous, minimal coupling in the bulk correspond to the non-homogeneous, okay? That is the distinction.
Maybe you mentioned this, but I have this question, like what is the motivation for doing these things in momentum space? Maybe you mentioned this, but I missed it.
Here in a couple of slides, okay? You will see the structures.
Okay.
Tilde was, sorry.
This is the epsilon, wild tensor with the epsilon, 4-dimensional epsilon contracted. There is also a nice interpretation of non-homogeneous and the homogeneous part. If you calculate correlation function in the free boson and the free fermion, add them up, that precisely gives you the non-homogeneous parity even. If you subtract them, you get the homogeneous. As you can see, inside the triangle, Watt-Takase identity of free boson and the free fermion are identical. So hence, B minus F will be homogeneous even, and B plus F will be the non-homogeneous even. And this also implies that the free boson written in terms of, in this language, non-homogeneous plus homogeneous, and free fermion is non-homogeneous minus homogeneous. Okay. And here, as you can see, it is tempting to put a phase in between the exponential of I theta, which interpolates between fermion and the boson. Okay. And we'll see, working in momentum space or spinor-helicity variable, precisely this is what we are going to get. Maldaceno's answer means this. Okay, that's what I'm going to show now. Yeah, I'm still doing the CFT analysis, and let me be inside the triangle for the moment. And this will also explain why I'm interested in the momentum space. What's the motivation or interested in momentum space versus position space? In momentum space or in spinor-helicity variable, you immediately see that the parity odd homogeneous structure and the parity even homogeneous structures are not independent to each other. Okay. For example, in momentum space, the parity odd structure can be obtained from the parity even structure by doing this simple transformation. Okay. And here I have given you an example of stress tensor 3-point function, but this can be generalized to any 3-point function of any spin. Sorry. In Poisson space, this epsilon transformation corresponds to a something very complicated integral transformation. And this is what I call as a epsilon transformation. As you can see, it's an integral transformation. That's why people did not notice it in Poisson space. But in momentum space, while solving conformal water entity, you just get this kind of thing. Okay, So what I wanted to emphasize, momentum space or spinor-helicity variables, there is an extra relation that you get. Earlier, the parity of structure that was thought to be independent, that no longer remain, meaning the parity of structure you can now determine in terms of parity event structure. Okay.
I didn't understand your notation. What is K1?
Yeah, sorry. So stress tensor at momenta K1, stress tensor at momenta K2. This is the 3-point function at K1, K2, K3.
K1 is a vector, right?
K1 here, so epsilon mu nu rho, I have contracted one of the epsilon indices of the epsilon with the K1 indices.
That's what you mean by.
And outside it is mod of K1. Outside it is mod of K1.
Oh, mod of K1.
Here, whenever it is appearing here, that is like one of the free indices of epsilon is contracted with the indices of the momentum.
Okay, so that's like the vector, I mean the unit vector. It's contracted with the unit vector in the direction K1? It's like K1 mu divided by...
No, yeah, if you do that, then it will become a unit vector here. But for the moment, I have written it just K1 mu. Yeah. Interestingly, if you convert this result into spinor-helicity variable, you get that there is just a factor of I relating. And in the complex conjugation, you will just get a factor of minus I. In spinor-helicity variable, this relation becomes extremely simple with a factor of I and factor of minus I in appropriate helicities. But as you can see, progressively, this relation becomes complicated. Spinor-helicity variable, this relation between parity even and odd is simple. Momentum space is a little more complicated, and Poisson space is very complicated. And we'll see this anyonic interpretation is most clean only in the spinor-helicity variables. Okay, this also gives a this is one of the good thing about in momentum space. So if I think from this perspective, let me rewrite again Maldaceno's answer or Prakash Gyambin's answer. They had 3 different structures. I'll rearrange things in terms of the homogeneous and non-homogeneous structure. In spinor-helicity variable, now I'm going to use this odd related to the parity even homogeneous, and then all these 3 structure actually becomes only 2 structure, one non-homogeneous and one homogeneous structure with a coupling constant becoming like it's a this way. The 3 parameters. Here it's a real number, gamma is a real number, and a phase. Okay.
Sorry, Sachin. No, normally when you say spinor-helicity, you have in mind massless, the mu and lambda that correspond to a massless vector.
I'll explain a little better.
Okay, because I was not understanding. Here you're off shell, right?
Yeah. So the way it is done is that this was introduced by in the context of cosmology by Maldaceno Pimentel. What you do is that you take massless 4-dimensional usual spinor-helicity, but in de Sitter you introduce one vector, one time-like vector. that relates this lambda and lambda tilde. And then what you get is a 3-dimensional off-cell spinor-helicity thing, and that is suitable for analyzing the CFT. Okay.
You go one extra dimension to make a massive thing, object mass.
Yeah. So K0, like the mass will be like the K0 thing. Totally, yeah. In 4 dimension, the K0 will be mod K. That's the thing. Yeah.
So you start with the 4-dimensional spinor-helicity.
Yeah. Yeah. Right.
So you do not express the currents in terms of the spinor-helicity variables, but the final result that comes in terms of the momenta, right? Or do you express the currents themselves in terms of the spinor-helicity? Because I don't think
in spinor-helicity variable will have its spinor indices like minus plus all those indices, spinor-helicity indices, and what I'm doing is structures will be here. What I mean is the structures, okay? Really the momenta or helicity structures, okay?
Yeah, so when you evaluate the correlator, the expression that you get in terms of the momenta will be expressible in terms of the spinor-helicity. Is that what you mean?
Yeah.
Okay.
One thing you immediately see here, if NB, if for a supersymmetric theory, if NB is equal to NF, you immediately get 2 structures, okay? And this was conjectured earlier in the literature that for supersymmetric theory, there are 2 structures. But in this language, it becomes very easy to see, and which part of the correlator is not present also becomes very easy to see. Yeah, so this gamma will be, I make combination of NB, NF, I take out NB plus NF all throughout, okay, that I call as CS. Then NB minus NF by NB plus NF and N odd by NB plus NF, I combine them to make it this complex number, okay. Because this odd structure and these structures are related by a factor of pi, as I just saw, okay. Now, if I apply this result for Chern-Simons matter theory, you get a very simple looking answer, as I was pointing out earlier. You just get a phase here, okay? So you have a non-homogeneous piece, homogeneous piece, and a phase. I want to also emphasize here one very important point, that this non-homogeneous piece and the homogeneous piece, you can just identify from either free boson or just from the free fermionic theory. You don't require both the theories, and hence, this Chern-Simons matter theory 3-point function, you can just obtain from just the free bosonic theory or free fermionic theory by appropriately multiplying with a factor of exponential I pi lambda, okay? So what I'm going to show today by the end of the talk is that not only 3-point function, here I'm just doing 3-point function using simple conformal water entity, the conformal water entity momentum space, and I get this kind of results. But if I go to 4-point function, there I won't be able to use conformal water entity because that language is not yet very well developed. But what I'm going to use is slightly broken higher spin symmetry, and I'm going to come to exactly similar kind of result. Rather than in the non-homogeneous and the homogeneous language, the proper language I'll be coming to in this language. So re-expressing this non-homogeneous and homogeneous in terms of free boson and the free fermion, this is the structure that you get, okay? The 3-point function, if I know the free boson and the free fermion answer, add them up, subtract them, multiply with the appropriate factor, you are going to get the 3-point function. And you will see precisely the similar structure also happens to be true at the level of 4-point function or a higher point function, okay? That's what is the central result. This already includes the odd piece. Odd piece comes due to this phase factor. If you open it up, that phase factor will be, imaginary factor will be absorbed here, and that will make it odd. So this anyonic phase, I call this anyonic, that's the reason this talk I called anyonic. This anyonic phase interpolates very nicely from free boson to free fermion. If lambda is equal to 0, you see that you get the free bosonic answer, free fermion cancel out. Lambda is equal to 1, you get a free fermionic answer. At lambda is equal to 1, exponential of I pi is equal to -1. So you just get the free fermion. So that's why I call the anyonic phase, interpolates nicely between the free boson and the free fermion. And in fact, in spinor-helicity variable makes this conformal collider bound also very, very intuitive. And the conformal collider bound, now actually, this is a space of the coefficient of the homogeneous function, gamma is exponential I theta. At theta is equal to 0 and gamma is equal to 1. That is the free bosonic theory. Gamma is equal to -1, theta is equal to pi, and gamma is equal to 1, free fermionic theory. And what interpolates here, the unit circle is interacting higher spin theory or Chern-Simons theory. And conformal collider bound says that all the CFT has to lie inside this circle. Holographic CFTs will lie even more inside the circle. And you see that the space of the CFTs are saturated by this Chern-Simons slightly broken higher spin theories or this higher spin theories, okay? And this is a conformal collider bound. So, conformal collider bound is on the homogeneous coefficient, and this is what is being shown here, okay? Now, the story outside the triangle.
I have a question.
Yeah.
Like the higher spin theory, by the higher spin theory, you mean the Vassiliev, the ADS dual to the conformal field theory, right?
Yeah, when I'm saying, yeah, exactly. Those are the theories.
So are you going to derive the corresponding correlators from the Vassiliev theories as well, as is done in normal ADS CFT canon, or you're just going to say that it's dual?
I think some of those derivations were done earlier in the Poisson space, but the correspondence is well established there. So what I'm right now doing just the momentum space, CFT analysis. Okay.
Okay.
Now, going outside the triangle, you see something very interesting happens. Outside the triangle, I discussed that there is only parity even structure when it is conserved. But let's say the outside the triangle, the parity of structure are also defined through the same epsilon transformation. So the Ward identity for parity of structure is the epsilon transformation of the this free boson and the free fermion Ward identity, this subtracted version. As you can see, inside the triangle, Ward identity for boson and the fermion are identical. So this is just 0. That's why the parity of stuff is a homogeneous structure inside the triangle. But outside the triangle, these are not same. So you will get something. Okay. And that's something, I'm not going to show the details because of lack of time. That something turns out to be exactly identical to what you do in the here. Take the free bosonic answer, take the free fermionic answer, just do the epsilon transformation, you get something, and that answer precisely matches with the independent calculation that you can do by considering by calculating Ward-Takase identity that you get from calculating the Ward identity coming due to the non-conservation of the higher spin current. Okay. So, for example, for J4, this thing, if you calculate the Ward identity, it will contain, as I said, J1, JJ 2-point function, product of JJ 2-point function. That is here. But by doing this epsilon transformation, I'm able to reproduce that just starting from the conserved Ward identity, conserved current Ward identity, I'm able to reproduce the non-conserved Ward identities. Okay. So, in that sense, yeah.
I forgot what was the epsilon transform.
Yeah. Maybe I have actually written it here.
The momentum space is epsilon times k.
Yeah.
That's okay. That 1 over k1
epsilon. Yeah. So let's so.
Okay. So yeah.
So just to give you a little intuition, the Ward identity, if there are conserved current, contains its delta functions, right? Now, in Poisson space, the epsilon transformation contains this integral transformation. As you can see, this integral transformation will remove this delta function, and it will make it precisely the same as the Ward identity of non-conserved current. Okay? So, in this sense, the slightly broken higher spin theories are very, very special, in the sense that just I can identify them starting from the exactly conserved higher spin theories. Okay, that's the in that notion. So I'm now going to first show that how this results actually can be very interesting if I go over to the 4-point function. Okay. So first I'm going to do a very naive analysis of the 4-point function, and then I'm going to make them precise. Oh, yeah, sorry. Let's consider T. Let me just give you one example. I think that will be fine. So let's consider the example of JJOO. Okay, this correlator was not computed because it's a very complicated calculation using either higher spin equations or using direct computation, Feynman diagram computation. This 4-point function. However, there is when I say not computed, what I mean is that this correlator was computed in a very, very particular kinematics and only for certain, for example, certain in the light cone coordinates, and in very special kinematics, this correlator was computed by summing over all loop results. But what I'm going to show is a much more general result by naive analysis that using the results at the level of 3-point function.
O is the scalar.
Yeah, here O is the scalar and J is the spin 1 current. So first thing to note that if there is a 3-point function involving J spin S current and 2 scalar, then the 3-point function in the free fermion and the critical bosonic answer are identical. If there is only 1 spin S current, okay, the structurally they are just identical, okay. Now let us consider JJOO in the quasi-fermionic theory or in a Chern-Simons matter theory. So I'm just doing a naive analysis. So I'm just going to break this up into with a spin S exchange. Okay, JJJS with JSOO. All these are in the quasi-fermionic theory. Now using Malda-Sena's result, I'm going to rewrite JJJS in terms of 3 structures: free fermion, critical boson, and the parity out structure. Now the result that I discussed earlier, I'm going to rewrite that parity out structure as a epsilon transformation of free fermion and the critical boson. Note that the critical boson and the free boson for all non-zero spins are identical. So I'm not going to make any distinction. So I have just used the JJJS 3-point function. I have just replaced 3-point function using the epsilon transformation. What I'm now going to do, I'm just going to take JSOO and put it inside, okay? So then I get the first structure JJJS with JSOO. This part, I get this first part. Then the second part, epsilon transformation of JJJS with JSOO. This is the second part. The third part, epsilon transformation of critical boson and JSO free fermion. Here what I have done, I have used this relation. Free fermion goes to critical boson. And then I have also written the last term, JJJS critical boson with JSOO free fermion. Now I'm using this relation to replace, okay? Now you see this structure, I can rewrite as JJOO free fermion answer. This structure here, I rewrite as a JJOO critical boson. And then this structure, these 2 structures are precisely, this structure becomes JJOO free fermion with the epsilon transformation. This structure becomes JJOO critical boson with the epsilon transformation. So this is the result that you get, okay? Earlier, if you did not knew odd in terms of free boson and the critical boson, you could not have done this analysis. But knowing this helps us to get this result, okay? When you have 2 scalar insertion, but if you don't have another current here, then they will not be identical. Sorry? No. Once this is free fermion, meaning no Chern-Simons here. So when you apply Chern-Simons, you get 2 structure already.
So the free fermion, if you gauge the favor to using Chern-Simons, then
yeah, it will have both the structures with coupling constant. Yeah. So here it's
allow you to calculate the correlation. I mean the 4-point correlation function in an easier way.
Yeah. So here I have just given you a very, very naive analysis. For example, I have not spoken about double trace contribution, etc., many things. But as you will see, this result actually I'll do a totally different analysis and I'll land onto the same result, exactly the same result. But this gives an intuitive understanding why this result works.
No, but does it help to? I mean, you said that JJO was very difficult to calculate. Does this help to calculate it in any easier way?
Well, I have already calculated, right? So now, if you just do a perturbative calculation, then you will be able to see that they should match. So, for example, as I said earlier, in a very special kinematics, it was done, and in that very special kinematics with some particular components, one can check that actually this is this matches with this.
No, if it's already calculable, then what's the point of breaking it into 4 terms and doing this analysis?
So as I said, already calculable meaning you calculated just JJOO also in a very particular kinematics, and you did not understood what is the structure look like. But here, what I am giving is a generic structure that even before calculation, this is the answer. The answer was what you got earlier is a 1-page long answer, but right now I'm just showing a one line answer. Okay, that's the difference. Yeah.
The critical boson is also known.
A critical boson, in momentum space is very easy to compute. In Poisson space, it's an integral transformation. But in momentum space, it's just some multiplication with some momentum.
That can be computed.
Yeah, that can be computed. That's not a difficulty. This is at large n only, and you can show that at finite n, of course, is very complicated. But at large n, it's an easy calculation. It's not a difficult calculation.
What do you use? You cannot use fixed theory.
No, first you calculate the critical boson theory, and then you get a result. Now, because first you calculate in the free bosonic theory, then you know how to go to critical boson by doing a 5⁴ deformation. Then you can actually find out which diagrams contribute. And if you take a large n limit, you will be able to show that it comes out in momentum space. Maybe here multiply with a factor of K3 and K4. That's all.
So this is done in the combination of large n and epsilon expansion.
No, just large n. Just large.
It's a Legendre transform.
Legendre transform. It's a Legendre transform.
In large n, you use the factor in large n, it's just a Legendre.
Yeah. So, we have till now used conformal field theory analysis, purely CFT analysis, but the result that I showed there for JJOO, not only JJOO, for arbitrary spin, I'm going to use slightly broken higher spin equations, and that is going to give me all those results. So before going to that result, let me just, how much time do I have?
How much time do you need?
Yeah, what I'm planning to show is first, I'm going to just show the results, and that will take 5–10 minutes, and discussing it will take some time. Okay, so you tell me.
15 minutes is okay.
15 minutes, okay, fine. Okay, so I'll be a bit quick here. So let me then just mention the method that is used. Okay, just I go to the results, okay, first, because that's more important. Yeah. So, basically the rough argument that I have used in my analysis in the paper that I have written recently is the following, that, as we saw at the level of 3-point function, I could map those parity or the part to parity, free fermion and the free boson. Okay, so now and then I also showed that this slightly broken non-conservation also I was able to determine in terms of the conservation. Now, what Maldacena did was that he did an analysis using the higher spin or slightly broken higher spin equations. What we did is that took those equations, did not try to solve them because that's very difficult. Just took those equations and tried to rewrite those or map those equations to just exactly conserved higher spin equation, meaning the free fermionic higher spin equation or the free bosonic higher spin equation. So we did that mapping, and while doing that mapping, it was absolutely important that we work in momentum space or in spin-helicity variable. And using that mapping, we got these results. Okay, so I have not for 4-point or higher, I have not explicitly computed what are those correlator look like in momentum space. But what I have done is that I have just given free theory answers. I'll be able to compute the interacting theory answers. That is a map that we have done. Okay, so let's see. Let me show you results starting from 2-point function. At the level of 2-point function. I have free fermion and a parity odd piece, which is also epsilon transformation of the free fermion. In spinor-helicity variable, they take again a very simple form. Okay, this is at the level of 2-point function.
Lambda f is proportional to lambda tilde.
Yeah, lambda f is proportional to lambda tilde. Yeah. So this is the lambda of the Chern-Simons matter theory tube coupling, and in the SUN. Okay. Yeah, for 3-point function, this is the momentum space expression. This is spinor-helicity variable expression, and one can rewrite this expression also in terms of this. Okay, this I have already discussed in details. So I just want to emphasize one more thing. In 3-point function, this answer looks like that the Chern-Simons matter theory would require free fermion and the free boson answer both. But here what I have tried to emphasize that actually if I just know free fermion answer or the free bosonic answer, I'd be able to reconstruct the 3-point function of the Chern-Simons matter theory by identifying non-homogeneous and the homogeneous part. Okay, so this is the significance of this result. So at the level of 4-point function, this result was already known earlier. Scalar 4-point function. This result was also known for stress tensor and the 3-point function. But this is a result for 2 spin S1, S2. This is a result exactly the similar structure. Please look at this 4-point function of S1, S2, S3, S4. This is the full answer. Okay. So I would, because I did not show you the analysis, I would like to mention one thing is that the proper claim is that this is one of the solutions to the slightly broken higher spin equations. There might be more general solution, but it was not possible to identify them explicitly. But this is one of the solution, and by doing explicit computation perturbatively, we have 2 evidences like JJOO and JJJJ, all spin 1. That there is these answers are actually working nicely. Okay.
The thing that confuses me is that the 3-point and one you quoted in terms of free fermion and free.
Yeah.
But 4-point you're quoting in terms of free fermion and critical.
I'm sorry. Here whenever there is non-zero spin, this is a typo. A free boson and the critical boson doesn't matter. If there is a scalar field, then only it will matter. But as I said, that transformation is very trivial. Whenever I'm talking about quasi-fermion, I really mean free fermion and critical boson, not really free boson.
Okay. So I should just interpret also the 2-point function answers in terms of that.
Yeah, 2-point function is very trivial. Yeah. 2-point function, free fermion, critical boson, all are just identical.
2-point function and 3-point functions are in control field theory determined just by
symmetry.
Yeah. Normalization.
Yeah. But the great thing about that, even the 4-point function, which could have been much more complicated, that also looks like determined in terms of free theories. Okay, free in the sense of critical bosonic theory and the free fermionic theory. Okay.
What is the point of separating the free fermionic? I mean, considering the combination of the free fermionic theory and the critical bosonic theory at the same time, can't you just simply consider the free fermionic theory on its own and compute the correlation functions and consider what dual theory exists? What is the point of mixing the two and then separating the two?
Mixes is that if you couple Chern-Simons with the free fermion, then the answer that you get is a combination of free fermion critical boson. It's not just the free. So if you are just calculating in the free bosonic theory, for example, if you set lambda tilde to 0, you will see the free fermion. Okay, but here we are not working in just in the free fermionic theory, in the free theory, but we are working with a fermion coupled to Chern-Simons, and then all this structure automatically arrives. I'm not putting it by hand. Okay.
No, but I mean, the fermion doesn't have a correlation function with the bosons, right? I mean, fundamentally, they are not correlated with each other. For instance, the electron doesn't, I mean, in a QED theory, the electron doesn't have a correlation function with the photon. I would suppose here also something similar works.
Maybe we can postpone the question to last.
Sorry?
I'll answer your question in a later. So this time is a little short, so I'll just answer at the end when we discuss this. Okay.
Okay.
Thank you. Okay, so actually this story you can, yeah, this is 4-point function. You can actually play this game even at the 5-point function level. So, you know, what I'm doing is that given a scalar, any n-point function, that input I require. This actually, in a previous paper, we computed for some other reason. If you give me that input, I'm going to put it in the higher spin equation and then going to generate these results. So you see, that is how the higher spin equation should be. Like higher spin equation should relate cohesion function with spins with the cohesion function with the non-spins. So you know, as I said, this is one of the answer. You know, there might be more answer that you can add. For example, there can be answer at the level of 4-point function, which are ADS contact terms. That is what we are investigating right now. The reason I'm saying this is that the analysis for JJOO that I showed was using the single trace exchange, which leaves you know, contact terms ambiguity. But you know, those things are separately we are trying to investigate. You know, what we have to do is that any extra thing I have to put in the equation and show that whether that satisfies or not. Okay, that will be, if they satisfies, I'll be able to add them here. Okay, so that is the thing.
So those things will be homogeneous solutions.
Those things will be yeah. Oh, homogeneous. Sorry. Yeah, exactly. Those things will be homogeneous. Yeah, yeah.
So the point is that the homogeneous solutions for the 4-point.
Yeah. Those has to be homogeneous because this has saturated all the word identities.
But in general, you would expect those terms to be present, right? I mean,
the contact terms. Yeah, in general will present, but I'll give you some evidences. For example, OOOO 4-point function. If you do this naive analysis, you expect this contact term, but if you and OOO, you can also calculate perturbatively, and then you can show that the coefficient of those contact terms are just 0. Similarly, for TOOO, this is also true. For JJOO, that also looks like to be true. So you know, that's a. So we are currently investigating that, but it looks like that maybe they are just 0 for all this. So I'm going to discuss this TTTT, this 4-point function. You can show that by doing some analysis that it has 5 different structures, okay, in quasi-fermionic theory. Now, using slightly broken higher spin equation, which I have not really shown you how to do that analysis, you can show that, you know, you can show, one second, you can show that these are the 5 structures, okay? These are the 5 structures that I have determined. But let's concentrate on this first 3 relation. X4 is equal to TT, let me just show once. Yeah, so here, this X4 should be of the critical boson, X0 should be free fermion, then there are 3 more structures to be determined. By doing simple slightly broken higher spin equation analysis, you'll be able to show that X3 has to be same as X1, and X2 is something that you have to determine. And you know, and this is what look at these things. These structures was for if you could have done for JJJJ. In Rohit Kolar in his paper computed JJJJ in a very special kinematics, and as I said, like it's very difficult to compute those. And he actually observed these relations already that we could derive more generally for any arbitrary spin just using you know, higher spin analysis. And then X1 actually is supposed to be this extra structure that actually currently we're just trying to check whether his answer matches with this expectation or not. Okay.
Is there a sense in which you can think of your answer as coming out of computing Witten diagram with some bounded properties?
Yeah, that's yeah, that's a good question. So I think it should be Witten diagram with some twist, which sums over all possible twists. Sorry, is a Witten diagram. Witten, if there is an analog of twist Witten block, meaning what I mean is that suppose these are all you know, these theories have all the higher spin currents, right? So for example, if I take JS, it has dimension delta is equal to S plus 1. So the twist is equal to 1. Now, if I can sum up all those twists,
all those twists to
yeah, all those twists to one operator, and then maybe other twist operators, they will correspond to, I think that's the proper way to, from the CFT analysis, if I'm sure that will have a proper interpretation. But right now I see in the literature, no one has even calculated, maybe my ignorance, the spinning twist blocks, okay? And the Witten diagram analog would be, I think, if I have an analog of how to calculate them. Okay? That's what I think.
But could you, I mean, knowing your answer, could you try to reconstruct what the Witten diagrams would be?
Yeah. So, in the bulk, if I try to write down, let's say, terms, let's say I consider the simplest scalar 4-point function. Okay. The scalar 4-point function contains OOJS, JSOO. Now, if I look at the 3-point coupling in the bulk with a 2 scalar and 1, spin S thing, that will also contribute the 3-point coupling, and there will also be contact term in the bulk. This, I think the OOO, that contact term in the bulk, that you can identify from the Witten diagram. That you can actually compute that in the. Just given this answer as you asked, I'll just show it here in one. So, what I mean is that there will be this plus this kind of Witten diagram. Now, these parts will be related to a particular twist block. Sum over all, some particular twist I sum over something. So this part will be related to that Witten diagram, and this part will be related to the contact Witten diagram. Now, from the CFT, if you are able to actually identify this part, which should not be very difficult, then if you have the full answer, if you subtract, then you will be able to identify this answer. For example,
but the ambiguities that you have possibly, right? Those are of the contact term type or not? There can be other solutions. Those solutions will correspond to contact.
Yeah. Those solutions, yeah, as I was saying, if I try to the ambiguity that I was talking about, those are you allow for ambiguity consistent with the Regge boundedness. Okay, there's some conjecture. Then you only allow for scalar. There are only 3 contact terms, and you can show that those 3 contact terms coefficient has to be 0, meaning. Already the scalar field answer that I have written down also contains this contact term answer already. I don't need to put another ambiguity. What I was saying is that this part also you can identify if you can just identify this part separately. And actually this is a very important exercise that was done in 2017 by Charlotte and Torona. In fact, what they showed is that these contact interactions are as singular as this, meaning singular in the sense you would think that this contact diagram coming due to just a contact term here, but the singularity structure is that of an exchange diagram, and hence they concluded that the Vasiliev theory is non-local and hence not very, very good theory. That was one of the conclusions by doing this. But just to sort your answer, I believe if you can just do this, then you'd be able to identify this by understanding the CFT part a little bit. Yeah, so as I said, reproducing this result using bootstrap, twist conformal block for spinning, etc., will be really an excellent thing to do. We are trying to think about these things right now, but very slowly. There's one more very important thing is that the results indicate that there has to be some simple reformulation of Chern-Simons matter theory at large N. This also connects to what Naveen and Siraj they did. They computed partition function, etc. Just from free field theory analysis with a little bit of tweaking, they were able to reproduce the partition function answers. So here, the 3-point or the 4-point answers also seems like just free theory answers with a little bit of tweaking. So it says that there has to be a simple reformulation of Chern-Simons matter theories. These are the theories that I was calling as a anyonic theories. So maybe you have to change the commutation relation, or you have to do something. And then at the end, that will be free theory. I have a free theory with a non-trivial commutation, different kind of commutation relation. And then if I just do a weak contraction, I'll be able to compute these results. Okay, that is what it looks like. And this is something very interesting to investigate. One more comment is that if you try to do a perturbative analysis, in general, doing perturbative calculation is very, very complicated. But the answers that I have shown in most of the cases, if I just go up to one loop, the answer looks like one loop. In one loop, I am able to reproduce all possible structures. Okay, so one possible way to verify the answers that I have is to work in the covariant gauge, and just compute at one loop. That calculation is already also a little complicated. But that is one possible calculation that one can do. At the level of 3-point function, this is supposed to, it's just going to work, because at the level of 4-point function, this is something it will be nice to check. Yeah, so here what I have just shown is that suppose you are calculating 3-point function in a quasi-fermionic theory, here insertions are the currents. You just calculate in the free boson, free fermion, and then, this is just a symbolic representation, nothing more. But what I just wanted to mention is that you can just go up to one loop and then you will be able to check the full answer, okay? Yeah, this already I mentioned paper. Yeah. So one more thing that you can try to understand is that, can I systematically start from the results of Chern-Simons matter theory and then go back to, in the bulk, can I try to find out a gravity dual? This was an exercise recently done by Aharoni, Chester, Urbach, for just the free theory. Starting from free theory, they tried to write down, construct the gravity dual. For Chern-Simons, and one of their ingredients was correlation function. Now, Chern-Simons matter theory cohesion functions are also returnable in terms of free fermion and the free boson. So it looks like that exercise might be possible to do, repeat. One might be able to repeat their for Chern-Simons matter theory. The only problem is that in their analysis, they did it in the Poisson space. And Poisson space, the relation that we have got will be some integral transformation. So, that's just, I wanted to comment on that. These are already, I have said, there are maybe another is a bootstrapping in the helicity variable or looking at the momentum space 4-point function, the homogeneous, non-homogeneous distinction, etc., will be very interesting. This is something right now looks a bit complicated. We are trying to understand in a simple one-dimensional setup, and later on we'll go to the high-dimensional setup. Supersymmetric extension and relation to this, ABGM theory kind of thing. One more thing that we checked was that if I do start with the higher spin equation, if I do some certain relevant deformation like mass deformation, etc., still the correlation function at the level of 2-point function was satisfying this higher spin equation. So probably we should also be able to actually extend this kind of analysis to massive case or temperature with the finite temperature case, etc., Okay, so at finite temperature, Omyo did some calculation. Those looks very complicated, but somehow it feels like that maybe using the free theory answer, you might just be able to reproduce those answers. Okay. Yeah. So
what you're saying is that you go to momentum space coordinators in the permanent theory also in terms of free fermion.
Yeah, I do not know, but maybe it is possible. At least in the massive case, the higher spin equation, we were able to modify higher spin equation and then check that the higher spin equations still are working in the free theory, not in Chern-Simons theory. So yeah, I'll not go into the details unless some people are interested. How did I derive these results? So I thank you all for your attention.
Are there any questions?
See, in the case of n equals 4 super Yang mills, when you take current correlators, you can have the bosonic currents and the fermionic currents. And usually what happens is that unless you combine them, you don't get the result from the supergravity ADS Witten diagram computations. So is there something similar happening here, or?
I'm taking what I'm doing is that I'm just coupling the fermion to Chern-Simons. Okay. Now, if I couple fermion to Chern-Simons, I can calculate. I'm going to take the current to be just defined by, let's say, psi by gamma psi. I'm not going to redefine the currents, and then calculate that 4-point function or 3-point function using Feynman diagrams. Now, then you get some complicated result. And then that result will have all the critical bosonic, you can identify those results with the critical bosonic result, parity odd structure, and the free fermionic result. At the coupling constant 0, you will just get the free fermion. But because the presence of Chern-Simons, you will also generate the other answer. Now, from the bulk perspective, we were asking, from the bulk perspective, you have this Chern-Simons series are dual to be, Vasilyev A theory or Vasilyev theory with a theta deformation. If you calculate using that with a theta parameter, in the bulk, it should match. That is the claim. Okay.
So, what is your current exactly? I mean, in the Chern-Simons theory, what is a operator?
Yeah. For example, spin 1 current will be psi bar gamma.
Psi bar gamma mu psi.
Yeah.
And then why is it? Why does it receive? I mean, why is it entangled or entwined with the bosonic contributions?
Yeah, that's why I'm saying if you don't have any Chern-Simons, you will just get the free Fermion answer. You are right that you'll just get the free Fermion answer. But if you couple it to Chern-Simons, because of the loop corrections, you will start generating different, more complicated structures. It happens to be so that you can identify those complex structures with the critical bosonic answer and parity odd structure, as I mentioned, and that is why the duality works. That's the beauty of this theory. Okay, that's a very non-trivial fact about this theory.
Okay.
If there are no more questions, let's thank Sachin for a nice talk again.
Thank you.